Hello students, welcome back. Let's go to section 5, Geometry Essentials. We're going to cover these three topics, and the first is Pythagorean theorem. It goes like this. Whenever we have a right triangle with sides A, B, and C, where C is the largest, the hypotenuse, then we're going to get a squared plus b squared is equal to c squared. That's Pythagorean theorem. Now, why is that? If you look up the internet, then you'll be able to find two different proofs of Pythagorean theorem, possibly even more. This approach is employed by our textbook author, so let's talk about it briefly. We take 4 copies of identical right triangle with sides A, B, and C respectively, where C is the hypotenuse, and arrange them strategically like this, so that we get a big square of dimension a plus b by a plus b, so that its area is a plus b total quantity squared. And then we have a smaller square given by hypotenuse, which is highlighted in blue here, which has c by c, and that area is c squared. And finally, the original triangles. There are 4 of them, and each one has the area 1/2 AB, so 4 times 1/2 AB, or 2AB. And that's how you get the first identity, from the picture and the area. Now, from this point on, just break up the parentheses and simplify. From the complete square formula, we get plus 2AB, and then this plus 2AB come from 4 triangles. They cancel each other out, and in the end, what do we have? We have the desired result. A squared plus b squared is equal to c squared. Now here is very similar approach. It doesn't appear in our textbook, but I thought it was worthy because textbook has one complete square method. Here's another complete square method. Take 4 copies of identical right triangle, but arrange this time a little bit differently. Hypotenuse goes outside, so that big square here has area c squared. And then 4 right triangles has 4 times 1/2 AB. Now, how about the square inside? What's that dimension? The distance here is a, and b comes from here to there only, so the difference here is a minus b. So this green square has dimension a minus b by a minus b, so the area is a minus b total quantity squared. So that gives me my first identity, and breaking off the parentheses we have minus 2ab and then plus 2ab coming from 4 triangles. Canceling those 2, we get the desired result. A squared plus b squared is equal to c squared. Now what if b is longer than a? No difference here because a minus b total quantity squared versus b minus a total quantity squared, they're the same. We're taking square anyway. Here's the third proof, and this one is, to tell the truth, my favorite. Using dimension theory, we can decompose a right triangle into 3 pieces, and they are completely identical except for the size, the scaling. And therefore, their areas are proportional to the length of the hypothesis. And then this one is A, B, and C. So the area will be area of green plus area of pink is area of blue, the bigger one. And the areas will be Ka squared plus Kb squared equals Kc squared, where the proportional constant K will cancel out. So we have the Pythagorean theorem. And this idea here, area is proportional to hypotenuse square. This idea is called dimension theory, and it has something to do with a concept called variation, which we will study in section 2.5 toward the end of week 4. And that's another reason I like this proof a little bit better than the other proof. It is related to what we are going to do shortly. Okay, maybe not shortly, in about 4 weeks. Alright, so much for Pythagorean theorem, and let's go to some more proofs. area formulae. Area for rectangle, that's where everything begins. Whenever you arrange all kind of objects rectangularly, how do you count? Just by multiplication, and that's about it. Area is A times B. That's where everything begins. Now, how about triangles? Everybody knows the formula, 1/2 AH, but how about the proof? Well, let's do it. Let's consider acute case first, and then we're going to do obtuse case later. An acute triangle here, as you can see, can be decomposed into two parts, left-hand side and right-hand side, and both of them are right triangles. Now, what if I flip this with respect to this side and flip the other with respect to that side? Maybe you can understand it very well, so here is better picture. So this right triangle here in the left-hand side of the original has a copy, precise copy, right across, just upside down. And this right triangle in the right-hand side has a duplicate copy, right across, upside down. Consequently, this dotted rectangle is twice as large in terms of area, of course, as the original triangle, and so the area is twice of the original triangle. So to find out the area of the original triangle, we have to take half of the rectangle. That's how you get 1/2 of AH. Now, how about obtuse case? I could inscribe everything into a rectangle, but I don't have to. I have already a right triangle here, so let's inscribe it inside a right triangle. And right triangle is an acute triangle, so we already covered it. So let's use that. And here we go. Original obtuse triangle plus this green right triangle. And we had this blue outline, the big right triangle. So we can find the original area here by subtracting one from the other, and that's how you do this blue minus green. And then break up the parentheses, and then cancel out 1/2 BH, and we get the desired result, 1/2 AH. So that completes the proof. Either way, acute case or obtuse case. So we are done with the triangles now. And the next topic is parallelogram, and here's the formula for parallelogram. Area is AH, where A is base and H is the height. How do you prove it? There may be many different ways, but this is one way to handle it. Cut away this portion to the left and then paste it to the right, and what do you get? You get a rectangle. Same area, because we did nothing more than cutting and pasting. So the area is A times H. That was easy. Next, trapezoid. Here's a trapezoid, and the formula is 1/2 A plus B times H. How does it work? Well, we get the duplicate, the same thing, and then arrange it strategically like this, upside down. Then you get a parallelogram, which is twice as large. So the area of this original trapezoid is 1/2 of the parallelogram, so 1/2 of A plus B times H. Finally, circle. So we begin from circumference 2 pi r. As a matter of fact, this is a definition of pi. Pi is circumference over diameter. So diameter is twice the radius. So this is where everything begins. And then you have to prove the area is pi r squared. How do we do that? We can take these pi's and then rearrange like this. Take smaller slice, even smaller slice, or even finer slice like these. And then you can see these figures here, parallelogram-like figures here, those are evolving into a sort of rectangle. And then the rectangle has area base times height. And then what is this base? Down here or up there? They're given by the half of circumference. Look at this dark piece down there. Or you can look at these white pieces up there. And then same fashion, dark pieces, same dark pieces, and so on. So no matter what you do, down here base is actually half of circumference, pi r. Now, the height is a little bit trickier. It is tilted, but this is radius r. A little bit less tilted, but still radius r. A little bit less tilted. Eventually, it will stand up straight if you have really a lot. So what we have? Pi r times r, so pi r squared. Well, how do we change these approximation into precise equality? That's a good question, but we cannot answer that precisely yet. We're going to do it in calculus. Okay, so much for 2D figures. And how about 3D figures? Here's a volume formula for box. A times B is base area and C is height. So this is pretty clear. How about the surface area? You can get it from the net. You can actually fold this over in a piece of paper and create a box. So we have bottom and top, AB and AB, and side, height is C, so AC, AC, and then BC, BC. So add them all up, and that is the surface area formula for the box. If you have an open top box, then no top, so we'll just have AB, not 2AB. Next, circular cylinder. Pi r squared is the base area here, see, and then times h, so that's the volume. How about the surface area? You can get from the net. The side is the rectangle and top and bottom. Top and bottom, those are circles, so we have pi r squared, and there are two of them. And then how about the side here? Well, circumference becomes the width, and this is height. So 2 pi r times h, that's how we get the side. Circular cone. And we have base area, which is pi r squared, and then times h, and then we have to multiply by 1/3, and that's a bit tricky. Why 1/3? It has something to do with the dimension, as a matter of fact. For triangle, we multiply 1/2. For 3D triangle, we multiply by 1/3, and 4D version, 1/4. 5D version, multiply by 1/5, and so on and so forth. And then you can get surface area through a net, but it's tough to understand, so let me just move on. For sphere, please remember both of these formulae. We cannot prove any of those, so let's postpone everything until calculus. But remember the formulae. Volume is 4/3 pi r cubed. Surface area is 4 pi r squared. Polygonal cylinder. Here's an example. So base area, in this case, heptagon times height. So how to get the base area is a little bit different story. You can decompose those accordingly using triangles, so there can be various different ways. From the net, you can figure out the surface area as well. And same thing goes for cones. Again, we get 1/3. Difficult to understand, but you need calculus for that. And surface area can be calculated through the net. Alright, so much for section 5. I guess we are done with this preliminaries now.